Am I screen sharing the right thing? I am. Hot diggity. All right. Sigma, area, Riemann, definitely. So area, Riemann sums, and definite integrals is the conversation for today, folks. It's going to be super de-duper. So we're going to find the area under a curve. We'll be successful when we can find the area under a curve approximately and exactly in geometric cases. So in pre-calc, what do we use to approximate area under the curve? Rectangles and sigma notation. That's what we use. Oh, there's Elise. Sweet. Again, we use the rectangles, but we use the sigma notation to try to automate the process. Because while it's fine and all to have sigma notation, it's kind of a pain, or find the areas of rectangles. That's all well and good, but sometimes it's just a pain in the butt. Like, especially like the more of them there are, the more of a pain it is to calculate more rectangles. So sigma notation helped us automate that process so we didn't have to do that. Yay! But why did we set it up that way? Like, it's very intentional the way we set it up. So why did we set it up that way? Again, because we wanted to figure out a way to make the process more accurate and honestly more automated. And by doing the automation, it makes the approximations more accurate because you're not messing up doing everything by hand and then adding it up by hand, or with the calculator by hand or whatever. And then you're also, what are you doing? Oh, and so that when you do more rectangles, you can just change your notation to make your approximation in general more accurate. That's the idea. I was like, I'm missing a thing. Where's my mind? Where is it? There it is. Okay, so that's the idea there. So here are the most common rectangle approximations that we did last year. We did left endpoint rectangles, right endpoint rectangles, midpoint rectangles. We did very little of, but they exist. And then trapezoid approximations. Just kind of for general reminders on those. Because maybe it's not something you remember very well for whatever reason. No accusations, just like for whatever reason, you don't remember them very well. So for the left hand, what we do is we take the left endpoint of each of these subintervals. So like, look at this subinterval right here. We take this value, because it's on the left, use that to make the height of the rectangle. This, we use the right endpoint. We took the subinterval, took the right one, and use that to make the height of the rectangle. A midpoint, you don't take the left or the right, you go right in the middle and draw on the rectangle from that spot. Trapezoid, both sides connect, both sides connect, both sides connect. We also figured out by the end of the year that trapezoid approximation is exactly the mean of the left endpoint and the right endpoint approximations, which is kind of neat. It's like, hey, we already can do these because we already know them. It's not too bad. And I thought it was pretty sweet. So I like talking about it because I think it was cool. So those are the 4 different approximations we can do. There's 2 others, but we rarely use those 2, so I'm not going to talk about them. But again, as we said, after making the rectangles, we added them up. And again, to get the heights of the rectangles, we just plug the x values into the function to get the heights. Or again, if you had the graph, you could just, you could draw in the heights. Now, their technical name, which we didn't use at all last year for a couple of reasons, I'll tell you those in just a moment. They're called Riemann sums. A Riemann sum is just approximating area with regular rectangle or regular quadrilaterals, usually rectangles. And I include trapezoids, but technically they're not Riemann sums, but whatever, I don't care. But when you add up a bunch of rectangles to approximate the area under a curve, that's called a Riemann sum, because Riemann was an old white guy who came up with the idea and people attached his name to it eventually. So that's, you need to know that, because on the AP test, that's a piece of knowledge that they need you to know. They're never going to say, find the left endpoint rectangle approximation with 4 rectangles. What they're going to say is something like, find the left Riemann sum approximation with 4 subintervals, which just means find the left endpoints and there's 4 rectangles. Again, why do they do that? Partially because the AP test, they also test your knowledge on vocabulary and terminology and knowing what those things are. And that's how they can do that. So you should know that. Again, why didn't we call them Riemann sums last year? Very good question. Because you had emerging learning about that. Calling them Riemann sum is a fairly abstract thing. You look at that, you're like, I'm not really sure what a Riemann sum is. But when you first are told left endpoint rectangles, like, you kind of know what left and endpoint and rectangles are. Riemann sums, like, you from a young age, you know that sum is like adding, and maybe you don't remember it as you get older, but from a young age, like, we talk about sums. Like, I know my daughter's talking about sums a little bit. Like, she's not using the word yet, but some of her like work is using that terminology. So here are the general formulas we used last year to automate the summing of the Riemann sums, the left and right endpoints respectively. Again, this is what it looked like at the end of the year when we started trying to figure out, okay, how can we automate this more? Like, other than just setting it up and then plugging it in, how can we automate it even further? Like, how can I think as little as possible about how the setup works so I can just kind of literally just plug and chug? Like, how can I do that? And this is where we started getting to. And I'll explain these pieces when we get into the next part. So the question that I need to pose, and that I'm sure you have, is, but why did we spend time on this? And honestly, why did we spend so much time using this sigma notation and the area under the curve? Like, why do we do that? Like, so like, I don't do things without intentionality. And by that, what I mean is I either do something because it makes me laugh and I think it's funny, or I do it because I'm setting up something down the road. And I'm trying to set up something down the road. I'm trying to set up parallel structure for things that we're looking at this chapter. Which, by the way, I didn't have this chapter's folder open before today started, and I just have it open, empty, and like ready to go. So, but why do we spend so much time in this? So we're going to look into that. So this was like the right endpoint approximation. I know that because I'm starting not at the initial subscript value, but I'm starting one after that. So how did we increase the accuracy of this approximation? Like, if I had 4 rectangles, I could increase the approximation by, I don't know if you throw out the ideas, by adding more rectangles. Instead of doing 4 in that interval, let's do 5. Most of the time we didn't do that. We went from like 4 to 8. We just doubled the number of rectangles. We just keep doubling and adding. And the more rectangles we did, as you all were thinking, the better the approximation got. And if you keep going and do more and more and more, which the automation process allows you to do just more and more and more, then, folks, we're getting towards an infinite amount. Which, if you haven't figured out, like, that's a big part of calculus, is just talking about infinity quite a bit. And again, so what happens to this as different parts of this as n goes to infinity? And again, this expression, as n goes to infinity, or as we rather like to call it, the limit as n approaches infinity. There's more. What is this going to go and become? Waiting for the moment. Waiting for the moment. See, timing's everything. Showmanship. Definite integrals. When you let n go towards infinity, you get definite integrals. What the heck is a definite integral? Well, I'm going to tell you right away of looking at this. A definite integral looks like there's a little less going on with it, a little less to process than with sigma notation. There's a lot going on in that sigma notation. There's not nearly as much going on in the definite integral. But there is, it's just there's a lot of things packed in. So let's try to see how these two things are connected. Like, where do they come from? Like, where are the parallel pieces, the parallel structures here? So the first thing is the heights of the rectangles. Remember, it was f of the subscript equation gave us the heights of the rectangles of the different k values. Well, if we have an infinite number of subintervals, it basically just becomes f of x is the height of the rectangles that we're finding the area of. Big brain. What about the width of the rectangles? Right here and right here. Again, B and A, those were the, I will talk more about that, but that's the width of the interval that we're dealing with. And N was how many rectangles we were dealing with. As N goes to infinity, this number becomes closer and closer to 0. It effectively is 0 when N is infinity, though it can never reach there, but you know what I mean. So since even though it can never reach there, it's effectively 0. So the width of the rectangles is what we call infinitesimal. It's the closest you can be to 0 without being 0 is the idea of infinitesimal. So infinite is like super big. Infinitesimal is like incredibly small. They're opposites in that sense. Bigger brain. The interval we are trying to find the area for. So again, it's B minus A, and we can see that manifested in a couple different ways here, right? In the sigma notation shows up right there, right here, as we were calculating the width of the intervals, or width of the rectangles. It shows up in the sigma notation, or the continuous sigma notation, the integral symbol right here. We put the end of the interval on top, the beginning of the interval on the bottom. Biggest brain. So that's how the parallel structures are set up. We're not going to do tons of the transformation between these two things because there's one question on the AP test usually that deals with that, and it's a later question, and there's other things I'd rather focus on than like spending more than a day on something that you're going to see for maybe 2 minutes and doesn't contribute tons to your understanding. So we're not going to spend the time on it. Besides, we spend most of the time on this stuff in pre-calc, so we don't need to spend as much time on it in calc. But this is the definite integral. This represents the exact area, not an approximation, the exact area under this function from A to B. So sigma notation with Riemann sums gives us definite integrals when we let the number of rectangles go to infinity, as we said. Definite integrals give us the exact, not an approximation as we were doing, the exact area of a function under a curve from on the interval from A to B. For now, we are still just going to do approximations of definite integrals using Riemann sums, unless the area is a common geometric figure. And when we're approximating the Riemann sums, you only need to use sigma notation if you want to, like the discrete one, the one we used in pre-calc last year. You only need to use that if you want to. Otherwise, just write out the sum and add it up. If the area is a common geometric figure, then you can calculate the exact area, or if it's made up of common shapes, like a circle, rectangles, triangles. If it's something like that, then you can figure out the area. And I should probably move that around. But down there, So this is just kind of remembering some stuff we did. This is this is an example of writing out a left Riemann sum with 4 subintervals right down here on the bottom. And yeah, it's the exact problem we did in pre-calc last year, if you remember. Again, I just did the height times the width plus the height times the width plus the height times the width plus the height times the width. Then added all those up, and I got 6.75. Again, this already had the rectangles drawn in for you, and your practice will have them drawn in for you immediately. But as you keep doing them, you should work on sketching on your own paper and drawing in your own approximations. I was also going to show you. I had another one I wanted to put in there real quick. With 8. Thought about it after I did it last hour and should put that in. So just to kind of draw that up a little more. Again, here's with 8 left endpoint rectangle approximations. Boom, boom, boom. Here's the height of each of the 8 rectangles. And here's the adding them up. Notice what they did for this approximation. They knew the width of each rectangle is 0.25. So they just put the 0.25 out front, added these all up and multiplied them. That works. That's fine. The reason we did it the other way is just to keep paralleling the structure of definite integrals. But you can, again, do it however you'd like. I just want to keep showing you some slightly different ways to approach these things. Alrighty. Oh, I have one more thing I wanted to show you. All right. So your graphing calculator can do these things too. So I'm going to show you on Desmos from scratch, and then I'll show you on your graphing calculator. Let me do a new share. Nope. Okay. So in Desmos, if you just go to and the graphing calculator, not the scientific one, if you start typing in integral, INT, it sets up a definite integral for you. We're going to look at what's the area. So we were doing 1 to 3 was the one we were dealing with. So let's go 1 to 3. Whoop, that's not a 3. Of x squared dx. And there's your approximation, or there's your exact representation of that area. Technically, it's still an approximation because it's not a fraction. If it was a fraction, technically then and only then would it be exact. So it's kind of just, again, those little things, the mathematical aspects of stuff that we want to just make sure we're talking about and being aware of. So that's how you do it there. Here it is. And let's get the detached view. So I have it set up here, but I was going to do a different one. All right. To do it on here, if you click math, number 9 gives you a definite integral. So you can type in 1. Okay. Oh, I can. And then my function is going to be x squared dx. Boom. So Look at those comparisons. Again, it doesn't matter to me which of these two you do. The graphing calculator is the one that you'll always be able to do because it's not internet connected. If the AP test is online again, or it really doesn't matter. But if it's in person on paper, the graphing calculator is the one you'll need to know. If your graphing calculator doesn't have the updated settings, that's okay. I can show you how you need to set that up. It's not terribly difficult. It's just something you have to learn how to do. New share. Okay, practice. So something I want to talk with the practice. It was asked last time, hey, can we do some more of those Desmos activities? Totes. I'm probably not going to do them every day because we're still going to be doing like some talking and stuff and giving you some layouts and stuff. But the next time we meet, we're doing 4.6, which is trapezoid approximations. So that's going to take very little time to talk. So then we'll do an activity after that. I was going to have one ready for today, but I couldn't decide on what I wanted to look like without it being busy work. And I didn't want busy work. I want like an intentional learning activity. So I have to finish sketching it out, and hopefully I'll have one for Monday for you. Anyways, so I have another one planned for Monday. Then we have a quiz, and then the week's not done yet. So we'll look at all that stuff a little more next week. Is that what I want to say? Yeah, it is. Oh, I remember the other thing. So this is a combined assignment. So it's not two separate assignments. It's a single assignment. It's 4.2, 4.3 assignment. So this 260, that's from the lesson 4.2, which focuses primarily on the Riemann sums, the algebra that goes along with it, and area. You just need to worry about finding the area of the rectangles, adding them up, and showing that process. So that's 35 and 37 is just doing that. Left endpoints and right endpoints. You can see them sketched on there when you look in your book. 51 uses the midpoint of each interval. You don't need to use the sigma notation part of it. Just figure out what the midpoint of each little interval is and use that to calculate the heights. And then you can just multiply by the width and go from there. You don't need to use the sigma notation that we used from last year at all, unless you want to. Like, you totally can, but you don't have to. All right. That's the big thing. This one has a lot of definite integrals. There's some properties of definite integrals that you should know. I didn't include them in this because they're fairly straightforward and you just need to read about them. So I didn't feel like it was worth our time to talk about it right now. But make sure you go read that, because if you don't read that, some of the questions might be slightly more confusing than they need to be. I think that's all I have for you now. Unless you have any more questions, have a wonderful day, folks. We'll talk to you later. Hey, Evelyn, just writing them down.